Hey, this is Jack Jackson back again. Let's take a look at something we kind of looked at earlier in a way, two intersecting secant lines to a circle. In our earlier video in this playlist, we looked at the relationship among this angle here at X, where they meet, and the two arcs that it intercepts, whether they're like this, or if it's inside, that angle intercepts an arc, but then its vertical angle intercepts another arc. So we're looking at those two situations. This time I want to look at, let's put it in the interior to start with, and I want to look at some line segments from say A to X, B to X, C to X, and D to X, and see if we can look at the lengths of those things and see any kind of relationship there. Can you see anything that might work out? Well, let's look at this uh, activity that Tim Brzezinski put together. Okay, so in other words, we're looking at these numbers A, B, C, and D, and look at what we've got here. If we will make a chord there, that gives us a triangle. See that? Watch this. Make another chord there, and what does he suggest is happening here? These have to be like that. Okay. Is that something special about the way we've got this set up, or does that give you an idea of what to do for proof? We can change these things here a little bit. Seems to be still working. How about here? Oh, that should give you an idea. Looking back at my thing here, we can go ahead and put some chords in. Let's put those in there, for example, going from the end of this. The chord goes from the end of this arc to the end of the other one, and same way over here. And let's measure those line segments. So XA is right here, the green one. That's 8.41 at the moment. XB is 11.14. XC is 16.54. And XD is 12.48. Now look at the angles formed here. We looked at this earlier. The purple angle here, DAC, intercepts this arc, and it's an inscribed angle. So that angle has half the measure of that arc there. See, that arc has 8.87. This is half of that at 0.44. Some round off there, but those are half. Then here, similarly, this angle right here also intercepts the same arc. DBC intercepts the same arc. It's going to have the same measure. So those two purple ones at B and A are congruent. And similarly for this angle here at C and this one at D, that is ADB is congruent to BCA because they intercept the same arc here and they're inscribed angles. Of course, you get a pair of vertical angles that are congruent too. So it's definitely you can get all three corresponding pairs of angles congruent. That makes these two triangles similar. What does that give you? Well, that gives you, say, this side, the green one over the purple one, um, is equal to the, say, the red one over the blue one here, which means if you do some cross multiplication, you're going to get some things that match up. So here I just kind of did it by experimenting, taking all these distances, x to A, x to B, x to C, and x to D, and multiplying them by each other. Here's x to A times x to A, here's x to A times xB, xa times xc, and so forth. And if you look, do you see anything that matches up here? Let's see. Where do we see? There ought to be one somewhere that matches. Do you see it? Here it is, 139.06 here, right? So what is that? That's xa times xc. This one, that's the two along the same line, right? Along the same original chord across here, those two pieces, gives you the same as you multiply across here. XA times XC is the same as XB times XD. Those two are the same. See that? And so that happens. So that's what happens there. If we move it around, as long as we're inside X is inside this, it works out. What's also kind of interesting is as x approaches the side here, gets real close to the side, kind of see what's happening there. Okay, so we can look at that. That setup. And those two numbers have to be the same every time. Isn't that cool? So that's because we have the two similar triangles, the pair of similar triangles right there. Okay, let's look what happens if we move point X outside the circle to the exterior of the circle. And to get everything to match up, you want it like this. And here we have X to A, X to D across here, which is the full length, right? Not just from A to D, but the full length from X to D. And then X to B and X to C. So X to C, the full length across here is the 22.06. From X to B is the 5.38. Right? X to C is that one. X to A, that's the green one, that's 6.32. And then from X all the way to D, passing through A, that is 18.81 at the moment. Okay, so what happens if we start playing around with products here? Do we get anything? Well, let's find two that are equal in this table. Do you see in them? There they are. XA times XD. Look at that. Again, it's the ones on the same line there. X to A times X to the D is the same as this one, 18 point something. That's the same as this one. XB times XC. Well, that's the two on this side. X to B times X to C. Why is it true? Can you prove it? Well, once again, we're dealing with some angles. Okay, and let's look at what we've got here. We've got some interesting angles going on here. So since those are the sides involved, you should expect to see some similar triangles. And where they are is XBD versus XAC. Those are similar. Okay, how can we see that? We just got to show they have two angles in common. And if you look, see this one that's right now it's 0.29 radians. That's the angle AC, either ACB or ACX. That's this angle here. It intercepts arc AB, and it's an inscribed angle. And we have an inscribed angle at D vertex. That's the angle BDA, or maybe call it BDX, and it intercepts this angle AB. So those two have to be congruent. And they both share angle X, so that's another set of angles. So that means the other angles are congruent. DBX would have to be congruent to XAC. But we get the similar triangles, so corresponding sides are proportional. They're related by proportion there. So X to B over X to A, XB over XA is equal to XC over XD. Write that down, cross multiply, and you get to what we found, that XA times XD is equal to XB times XC. So really we kind of got the same result both times, right? In both times we took the distance from X to A and X to C and multiplied those. Those are the ones across here. And then we did and that was equal to multiplying X times X to B times X to D. And it got exactly the same result when you're over here. You take X to A times X to D and multiply it by X to B times, or it's equal to X to B times X to C distance. The labeling is a little bit different the way I've got it set up here, so that those didn't turn out to be exactly the same, but they are kind of the same because it's the two on the same line here multiply together the two distances on the same line here, all distances measured from x. Same way this one, multiply the two on the same line, the two on the same line this way, again, distances from x. It works out to be the same. So pretty cool, huh? Pretty cool stuff. So it comes from similar triangles, and so those proportion theorems give you that basic setup there. Let's keep going with this just a little bit. What happens? Let me go back here. Okay, what happens as this say this D and A approach each other? Okay, so what are we doing? We're multiplying the distance XA times XD, and that's the same as XB times XC. But what happens is this gets closer and closer together. Eventually it gets to the point where D and A are the same point. Then the distance from X to D and the distance from X to A are the same, right? And so you have a tangent line in that case. There are not really two parts to this. You just have the same part twice. So you get XA squared, okay, is equal to XB times XC. And actually the same thing works as you're approaching a tangent line over here. So if we ever get, they're both tangent lines, okay, I don't have it perfectly here, but it's approximately, then what happens is this side squared times, so XA squared equals XC squared, which means XA and XC are the same. So if you got two tangents from the same point external to the circle, those two line segments have to be congruent. In fact, if you now connect these up to the center point, you got yourself a nice little kite there. Okay, quadrilateral XA OB is a kite. So that's sort of that's a limiting case there. Okay, so this is actually a different um, GeoGebra applet, but it's the same basically situation. But this time I actually did make it. So this is for sure enough a tangent line there. And when we look at the lengths of some of the line segments there, we can see them XA, XB, and XC, distances from X. And we look at products of this. This time we know that XA squared, 8.67 times 8.67 is 75.13. That's the same as you get right here, 75.13 by multiplying XB times XC. So if you look at these two cells, that one and that one, they'll always be the same as each other. So we can change this up a little bit, and those are the same size. Okay, so far I didn't change the distance from A to X, so they turned out to be the same. Even though I am changing these two distances, their product stays the same number as I move it around. Okay, if I move this around, let's see, I can change somewhere in here. I can change, for example, the distance from X to A. Now we got a new number, but again, it's the same both places. And as I move this around, it doesn't change. While we're at it, let's go back and remember a couple of things that we did about angles. Okay, so if we looked at this and we have, okay, here's our setup, right? Why don't I get it set up right? We found some interesting things here that this angle X turned out to be well, let's do it in the interior first. In the interior, it turns out you just take the measure of these two arcs here and average them. We add them up, and that is the same as twice the measure of this angle X. You can see that here in the tables down here. When we were outside the circle, look what happened. We found the measure of these two arcs, subtracted them, larger one minus smaller one, and that's twice the angle measure. Okay, so that's what we had something earlier. So once again, I want to take this situation and look what happens as this kind of approaches a tangent line right here. Okay, now what happens is once you should get to basically the same result. You do this arc minus this arc, right? It's just that C and D are basically, I mean, yeah, was it A and D are the same point. So you're still doing the arc from the point of tangency around to here, minus the arc here, the minor one, and then take half of that, and that'll be angle X. So we should see that result when we look at the situation where we have tangents. So now you basically just have this red arc and the one there, the blue arc, and sure enough, it turns out to be the same thing. If you take the difference, you get twice the measure of the angle there. Same setup as before. And why would that work? Well, let's look at some angles here. Angle, I got to point out here just to name it, EAC is this red one. It's half of the red intercepted arc here. So is this the same as angle ABC. And this blue one here, ACB, is the same size as the angle XAB. This half of the intercepted arc, when it's inscribed, still applies even if one of the sides is tangent to the circle, not secant. Still an inscribed arc, still an inscribed angle, still intercepts an arc, still measure is half of that. Um, so we have this setup. Now what do we want to know? Let's see. We want to compare angle A to that. Well, if you look at this triangle AXB, this red angle here, angle B, that's angle ABC, half of this red arc here. That one is exterior angle. So it's equal to the sum of the green one and the blue one here. So solving for angle X, it's the red angle minus the blue angle. Blue one's half of this arc, red one's half of that arc. And so if we double angle X, we get the difference in these two arcs right here. So we can see that proof, and then we get that. As this approaches a tangent line over here, then what happens? Well, again, it's just this arc minus this arc, and then take half of that, and that gives you the angle there. All right. So there's some interesting things about angles and proportions, proportional line segments from circles, where we have a couple of secant lines, or a tangent line and a secant line, or even two tangent lines.